Oh, hello wonderful person. I heard that you wanted to discuss dark matter today. So, let's talk about it. Today we're going to discuss a really exciting and somewhat unusual study that presents us with a somewhat unusual map of dark matter around our own galaxy that potentially explains a lot of mysteries from the past few decades. And specifically, this new study presents us with a major shift in our understanding of how the galactic architecture around the Milky Way seems to be structured. With all of this being the result of this invisible dark matter that produced a shape nobody expected. With all of this essentially described in this study by Ewood Wempe and the team you see here. And once again, my apologies for very likely mispronouncing your name. And so let's discuss this new discovery in a little bit more detail and talk about why this is actually really important. But first, let's briefly discuss what scientists believed for a very long time and why it didn't make sense. And so for a very long time, the standard scientific view was that our galaxy resides in the center of a giant, symmetrical, and very likely spherical ball of dark matter. Something that possibly looks like this. And this would be several million light years across, and basically contain a lot of gas and a lot of additional stars and satellite galaxies, all of which would be kind of circulating around, until one day they all combine. But in the last few decades, a lot of high-resolution simulations, and especially galactic simulations that tried to recreate Milky Way and its satellites by using supercomputers, actually had a lot of trouble recreating all of this, with the data suggesting that this classical picture was potentially incomplete, or maybe even completely incorrect, suggesting that the shape of this dark matter halo was maybe not spherical, but something a little bit more flat, or something more bizarre. And that's essentially what this new study discovers. There's a very high chance that the dark matter halo kind of resembles a pancake, or essentially it's a kind of a sheet that stretches for tens of millions of light years. But how exactly was this discovered, and what exactly does this help us explain? Well, to find this, researchers used the method referred to as BORG, Bayesian Origin Reconstruction from Galaxies, a kind of a complicated data simulation framework designed to infer three-dimensional shapes by looking at the motion of nearby galaxies, but by also including the earliest light in the universe or the cosmic microwave background. This model was officially created back in 2019, and its purpose was three-dimensional maps based on the observations of the universe we already possessed. And so for this study, researchers used the data from the cosmic microwave background along with the motion of 31 galaxies, specifically satellite galaxies, in order to simulate the local environment. And in their simulation, nothing at first made sense, or at least it didn't make sense at first, until they started to change the shape of that dark matter halo from the assumed spherical shape into something that was a little bit more flat and a little bit more disc-shaped. And so here they discovered that all of the observations suddenly fall into place, at least when it comes to the local group of galaxies. That's the galaxies that include the Milky Way, the Andromeda, and the Triangulum galaxy. If the halo of dark matter is actually concentrated in a plane extending to about 30 million light years. Or just to rephrase this, all of the galaxies and all of the matter seems to be concentrated along a still invisible dark matter halo plane that resembles a kind of a sheet. And the thing is, if this is real, the existence of this sheet helps solve a lot of different mysteries in regards to the galactic motion in the vicinity of the Milky Way. And so let's actually talk about some of these mysteries that even today still don't have any solutions, and actually mysteries that even kind of questions a lot of physical models and modern cosmology. For example, for many years, astronomers noticed that a lot of nearby galaxies seem to be receding much slower than predicted. In other words, physical models predicted that the galaxies should be moving away a little bit faster. And so if the dark matter around us was a simple sphere, the gravity should pull objects toward the center in a very specific way that unfortunately did not match the data, or did not match the observations. Yet surprisingly, if this was a flattened sheet, here the mass that's further out in the plane, much farther away from the galaxy, exerts a kind of an outward gravitational pull that then offsets this inward force. And effectively this prevents these galaxies from receding, damping their speeds, and explaining the somewhat smooth, stable motion we observe. And that's mostly because this sheet is absolutely massive. As a matter of fact, its central plane seems to be at least twice as dense as the cosmic average, but the regions right above and right below it seem to be more or less empty. Or they essentially seem to contain empty voids. And this type of a galactic architecture seems to align perfectly well with what we refer to as a supergalactic plane. which refers to a somewhat known arrangement of visible galaxies that you can kind of see in this image. So basically here, many different galaxies seem to be mostly arranged on a kind of a two-dimensional shape, as opposed to be more or less equally distributed in 3 dimensions. Now obviously some galaxies are not in the plane, but the majority are. And so here the visible matter traces out the overall framework or the overall skeleton built up by the dark matter underneath. And honestly, I think this image right here presents this pretty well. And so basically here, imagine this sheet or this disk as a huge amount of dark matter that then starts to attract a lot of gas and a lot of stars that start forming galaxies inside of it. But because this dark matter pancake is so massive, it kind of controls everything inside, including the motion and the overall development. And though at first this might sound kind of hypothetical and possibly not really that important, turns out that if this is confirmed, this explains so much. It actually solves several mysteries at once. First of all, there's a mystery referred to as DOS, Disk of Satellites. This is a very strange phenomenon observed in the Milky Way and the Andromeda galaxies, where the majority of dwarf galaxies, or the majority of satellites, seem to be arranged in a highly flattened, co-rotating planar structure, instead of being randomly distributed like what we would expect in a normal isotropic distribution. And for many years, this was a major challenge to standard cosmology. As a matter of fact, for the Andromeda galaxy, roughly half of the satellites seem to form a very similar plane, which is now referred to as the Great Plate of Andromeda. It's actually visible in this image, even though it's a little bit difficult to imagine, but this is something we've known for a very long time. Here's actually one of the first images from 2006. And so the fact that these smaller companions were not scattered randomly, but lined up in a very specific way, suggested that something about our initial models was not correct. Yet the interpretation from this study and a lot of these new simulations show that these satellites and dark matter subhalos seem to create these flat formations and identical orientations because these satellites seem to fall into place along this dark matter filament that's shaped like a pancake, or I guess technically shaped like a very large sheet. And the idea of these flattened dark matter structures is no longer just a proposition or just a theory. It really seems to be some kind of a fundamental part of the history of the universe, because something similar has also been discovered in galaxies far away. As a matter of fact, by using ALMA, or the Atacama Large Millimeter Array, astronomers have discovered massive primordial galaxies forming inside trillion solar mass dark matter halos, when the universe was only about 780 million years old. It was reported in the study by Maroney and the team you see here, with the observations suggesting that many of these early galaxies were already surrounded by huge amounts of gas, forming these really massive halos, sheet-like in shape, that might have been the primary drivers for galactic formation. And so this was something that was already happening in the early universe, with very likely many galactic clusters formed in a very similar way. And many of these early galaxies were very messy. They formed stars at incredible rates and evolved very quickly. Yet somehow all of this resulted in highly ordered galaxies we see around us, which means that all of this had to be controlled by something. And that once again suggests that this sheet-like structure involving these massive halos was very likely the primary driver for galactic formation. And so essentially here, based on the observations from really far away, and of course the simulations of our own galaxy, we can now sort of confirm that the supergalactic plane seems to be real and seems to represent a major structural feature of our cosmic neighborhood. And it's basically a vast pancake-like arrangement that seems to stretch for at least 30 million light years, possibly more. And so in other words, just like stars in the Milky Way that are flattened into a galactic plane, it looks like many of the largest galaxy clusters seem to be also organized in a very similar formation. Although intriguingly, it seems to be almost directly perpendicular to the Milky Way's own plane. In other words, we're not directly aligned with it, and instead we seem to see it from a perpendicular perspective. Here's roughly what this would look like if you were to try to trace it, and more importantly, here are some of the members of this formation, with the biggest ones being the Virgo cluster, the famous Great Attractor, and at least several other superclusters. And a lot of these superclusters are actually really massive, with the famous M87 black hole being the center of the Virgo cluster. And the thing is, if all of this is confirmed, it also additionally solves some other mysteries in regards to galactic shapes. For example, it might explain the idea known as the missing spiral galaxies, or basically explain why certain galaxies look the way they do. So here inside the plane, where you have a very high density environment because of this dark matter and because of this gas, galaxies tend to collide and merge frequently, which then destroys their spiral arms and turns them into smooth elliptical galaxies. This is how we think M87 came to be and why it has one of the biggest black holes near us. But outside of this plane, the galaxies are more isolated, and because they're not always colliding, they're able to maintain their spiral structures. And so at the moment, this seems to be the Milky Way galaxy. It's not really in the center of this pancake and seems to be a bit on the outskirts. But the main idea in this case suggesting that even galactic clusters seem to be connected by this invisible pancake. And so essentially none of the galaxies and even none of the galactic clusters seem to be isolated islands. They all seem to be part of this very giant interconnected web of dark matter, but instead of just being strings like you see in this simulation, large chunks of this dark matter seem to be also pancake-shaped, or essentially very large sheets. And so here, understanding the true shape of this environment will potentially solve a lot of mysteries of cosmology that we cannot explain today, including the ideas known as the Hubble tension, and a lot of additional observations that sometimes question modern cosmology. But for now, it looks like we live inside a large sheet. Not inside a ball of dark matter, but instead a kind of a pancake. And if confirmed, this means that the evolution of our galaxy, including how much gas will flow into the Milky Way, might have been predicted incorrectly, and we may need to rework some of the models when it comes to the evolution of the Milky Way. And so definitely quite an exciting simulation and quite an exciting proposition. But it will probably take a few years to confirm this, and especially because we need more observations that can then allow us to map the dark matter more precisely. And so here, by creating much better maps and by looking at additional sources such as quasars, we may be able to map the true architecture of this region in a lot more detail. But until we learn something else, that's all I wanted to mention. Thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access and a few more things. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.